This is an overview of confidence intervals for regression coefficients. If we consider the linear regression model, y model equals a0 plus a1x, those coefficient values aren't known exactly. They have uncertainty that can be estimated. First, we need to define some variables we'll use. There's the sum of the squared error, that's SSE. So that's the difference between each data point, y data, and each model point, y model. That's squared, and it's summed over all the data points from I equals 1 to n, where n is the total number of data points. Next, the mean value of x is defined. That's x bar. And then the sum of squared x, SSX. Here, we take the difference between each x value and x bar, square it, and then sum it up. Now I'm writing down the total number of data points, n, the polynomial order, PO equals 1 for a linear regression, and the residual degrees of freedom, which is nu, equals n minus 1 minus PO. The next step is choosing a confidence level. Here I have alpha set to 0.05, and that's associated with a 95% confidence interval. Now we introduce the student t cumulative distribution function. This is at the heart of estimating the confidence intervals for regression coefficients. The student t cumulative distribution function is sometimes written as t CDF, and it has two parameters, the t values, and then also nu, the residual degrees of freedom. It's plotted on the graph, and what you can see is there's a range of t values on the horizontal axis, both negative and positive values, and on the vertical axis it goes from 0 to 1, and that's associated with the probability. Right at 0 for a t-value, the probability is 0.5, and then it increases from there. The specific t-value we want to find is the one associated with the confidence level alpha. I've written that here as t-val equals t-in, the inverse of the student t cumulative distribution function, and it has two parameters, 1 minus alpha divided by 2, and then nu, the residual degrees of freedom. On the graph, I've marked the 1 minus alpha divided by 2 point on the vertical axis. We can follow that line over to the point on the student t CDF, and then follow that down to the horizontal axis, and that marks the t-val that we want for our calculations. Once t-val is determined, the uncertainty intervals for the offset and slope can be calculated, and their equations are shown here. So for the offset uncertainty, we're looking at plus or minus t-val times the square root of SSE divided by nu times the square root of the quantity x bar squared divided by SSX plus 1 over n. For the slope uncertainty, it's plus or minus t-val times that same square root of SSE divided by nu, then that is divided by the square root of SSX. These confidence intervals are proportional to the root mean square error of the regression, and coefficients have less uncertainty for better fits. It's best practice to report linear regression coefficients with their corresponding confidence intervals, as shown here. And what that implies is a linear regression model is not actually just one line, but it's a whole family of lines with different offsets and slopes that fit within these confidence intervals.